Dear students, welcome you all to the Power Hour NEET 2025 session. This is Ranesh sir, and today we will be having a study of chemistry, haloalkane, haloarine, and alcohol phenol ether topic. So it is a very important topic over here. Many questions are asked in NEET examination from this topic. So let us start. So haloalkane, haloarine, first of all we will be discussing about them, and then after continue for alcohol, phenol and ether. So let us start with haloalkane. We also call them alkyl halide. They are denoted by Rx, where X will be halogen, fluorine, chlorine, bromine or iodine. So let us see first of all preparation of the alkyl halides, that is haloalkane. Preparation methods. In this preparation method, first of all we will be having preparation of haloalkane, alkyl halides from alcohol. So in preparation method, first of all we will be having from alcohols. We will be having preparation of haloalkane, alkyl halides from alcohols. So let us see. The first method I am taking over here, it is the best method. They are asking which is the best method for preparation of alkyl halide from alcohols. So this is the best method, and the first method which is best method is Darzan's method. In this we are having reaction of alcohol ROH with Darzan method. We are having reagent SOCl2. So you have to write the reagent which is used in Darzan method is SOCl2. So you are reacting it SOCl2, giving RCl plus SO2 plus HCl. So why this is a good method for preparation of chloroalkane over here? Why this is a good method for preparation? We are getting chloroalkane over here, chloroalkane. So why this is a good method? Because all these byproducts we are getting over here, SO2 and HCl, they are released, they escape out in form of gas. So the byproducts in this reaction, they get escape out in the form of gas. That's why Darzan method is a very good method. It is the best method for preparation of haloalkane from alcohols. So this is the first method which we call it as Darzan's method. Reagent is SOCl2. Okay. One more point I want to highlight. If only they have given SOCl2, it will follow SN2 reaction, SNI reaction, and along with SOCl2, if they have taken pyridine, then it will follow SN2 reaction. So this important note you have to remember, that if only SOCl2 is there, you have to carry out the SNI, and if they are having SOCl2 plus pyridine, then you will be having the SN2 mechanism over here. Okay, very important point, because in exam they are asking. So let us continue with the second method. So let us continue with the second method. So let us continue with the second method, that is from alcohol only by using PCl3 or PCl5. For bromination you can use PBr3 or PBr5. Okay, are you getting? Okay, okay. So now we are having second method. There we are having reaction of alcohol with PCl3 or PCl5. So let us see with PCl3. So ROH, alcohol, is reacting with PCl3. You will get RCl plus, see, by this method if you take 3 ROH over here, you can convert 3 ROH into 3 RCl plus H3PO3 will be formed as the byproduct. With PCl5 you are reacting, we can have 5 equivalents of alcohol reacted with PCl5 and you will get 5 ROH plus RCl plus H3PO4 plus H2O as the byproduct. Okay, so this is the another method of preparation of haloalkane, or you can say chloroalkane, from alcohol which we are reacting with PCl3 or PCl5. And the method, what is it? If you are reacting with PCl3, you can convert 3 equivalents of ROH into RCl, and if you are using PCl5, you can have 3 equivalents of ROH converted into RCl. Okay, so this is the second method where we are reacting alcohol with PCl3 or PCl5 to get haloalkane. So let us see the next method, third method. The next method, the third method, is by having reaction of the alcohol with HX-ZnCl2, anhydrous ZnCl2, which is called as the Lucas reagent. So third method is from alcohol by reacting it with Lucas reagent, and this Lucas reagent is nothing but this is HX plus anhydrous ZnCl2. Okay, so in this method what will happen? See, this reaction, we can see there is formation of, there is formation of carbocation, and you know that 3 degree carbocation is more stable than 2 degree than 1 degree. This is the stability order of carbocation. That's why what will happen over here, this is also test for 1 degree, 2 degree and 3 degree alcohols. If you react alcohol with HX in presence of anhydrous ZnCl2, mainly this anhydrous ZnCl2 is required only in case of 2 degree or 3 degree, sorry, or 1 degree, not in case of 3 degree. Why? In case of 3 degree, the reaction is very much spontaneous because 3 degree carbocation are very much stable. Okay, so anhydrous ZnCl2 is required only for 2 degree and 1 degree. For 3 degree alcohol, anhydrous AlCl3, sorry, anhydrous ZnCl2 not required. Okay. So what is the reaction? ROH reacting with HX, we will get RX over here plus H2O as the byproduct. So you are getting haloalkane over here from alcohol. Okay. So this was the third method of preparing haloalkane from alcohol, and we had reaction with HX plus anhydrous ZnCl2, which is a Lucas reagent, and by this method also we carry out the Lucas test. In Lucas test what will happen? This is Lucas test is for determining the degree of alcohol. Degree of alcohol. It is for determining the degree of alcohol. Okay. In 3 degree alcohol, you will get instantaneous turbidity. Instant turbidity, you can say instant turbidity. In case of 2 degree alcohol, you will get turbidity, or you can say cloudiness, in 5 minutes. And in case of 1 degree alcohol, you will get turbidity or cloudiness in 30 minutes, and that too on heating. On heating. Okay. So this is all about the third method over here, where we had the preparation of alcohol, of haloalkane from alcohol. So all the three methods were preparation of haloalkane from alcohol. Okay. First method was Darjan method, where we reacted with SOCl2. If only SOCl2 is there, it will follow SNI mechanism. SOCl2 plus pyridine, it will follow SN2 reaction, SN2 mechanism. The second method was alcohol reacted with PCl3, PCl5. And the third method was alcohol reacted with Lucas reagent, that is HX plus ZnCl2, and this is also a test for identifying the degree of alcohol, and we call it as Lucas test. Okay. In this there is formation of carbocation. So everybody knows the stability of carbocation, 3 degree more than 2 degree more than 1 degree. That's why 3 degree carbocation give instantaneous turbidity, and 2 degree will give in 5 minutes, and 1 degree in 30 minutes, that also on heating. Okay. So let us see questions they are asking from this section. So this is the first question. Product X is, so you can see PCl3 they are reacting over here, and this is alcohol. So what will happen? This OH will be replaced by Cl, and you will get haloalkane, chloroalkane over here. So A option is definitely the answer. I also told you you can take 3 equivalents of this, and you will get this 3x over here, and the x will be this one. So we saw this over here. Let us see the next question. Yeah, we are reacting this HBr with this alcohol. I already told you that in case of 3 degree alcohol, there is no requirement of anhydrous ZnCl2. You can look over here. This is nothing but Lucas test, or you can say Lucas reagent reaction. You are having Lucas test over here. What will happen? This OH will be replaced by Br. So we will be getting the A option as the answer over here. Okay. So next question we are looking. X reacted with PCl5 gives this, and HCl plus POCl3. So this is nothing but, you can see we are getting this chloroalkane, and here Cl is attached over here. Initially this was alcohol, and will be having the formula CH3 CH2 CH2OH. So definitely which option will be the answer? B option will be the answer over here. Okay. So next question. When cyclohexane is poured on water, it floats on water because. Okay. And this also they have written. So I think mixing of two questions over here has happened. We are directly looking what is happening. This is alcohol PCl5. What will it do? It will provide chlorine minus, which will substitute the OH, and you will definitely get first option as the answer over here. We now only studied about this PCl3 and PCl5. They are used for converting alcohol into chloroalkane. Okay. So next question we are having. So now we studied all about the preparation method of haloalkane from alcohols. Let us continue. Now I am having preparation of haloalkane from alcohols, and then let us prepare them from alkane. Now we will be having preparation of haloalkane from alkane. Okay. So what is the method? We already studied this in hydrocarbon chapter. That is nothing but monohalogenation. You already studied, dear students, about this in our last power hour session about the monohalogenation. In this, what is happening? You are given alkane and you are reacting this alkane with X2 in presence of sunlight H nu, and you are getting Rx plus Hx as the byproduct. See, this is the overall reaction which is taking place. Overall reaction. I also told you about the step-by-step reaction which are taking place in this: chain initiation, chain propagation, and chain termination. That was studied already in the hydrocarbon chapter. So I think you are having already the basics of this reaction. The main important point over here is this important note, that how many number of isostructural haloalkane products are possible. So we had already discussed this in the hydrocarbon chapter, that the number of different position of hydrogen which is present in the given alkane, that many number of isostructural isomers of haloalkane will be produced at the product side. So important note, they are asking how many haloalkane, and as I told you, I am talking only about iso, or you can say isomers. With which isomers? Structural isomers. They are asking us about, if they are asking us about structural isomer, how many haloalkane structural isomers are possible? You will say equal to different number of position of hydrogen present in the given alkane. Okay. A very important question we are going to solve regarding this concept. Let us see. So this is the very important question. Most of the students, they are unable to solve this question. So let us see. Number of monochlorostructural isomeric product which we are getting in this reaction. They are asking us how many number of monochlorostructural isomeric products will be obtained. So as I told you, the different position of hydrogens which are present in this given alkane, that many number of this monochloro structural isomeric products will be obtained. So let us draw isooctane, and this is the very big exception that students have to remember. What is the structure of isooctane? It is a very important molecule that you have to remember. You already know this is the iso, but the most important interesting part is mainly students what they think that this is the iso part and we have to just add CH2 CH2 to get the isooctane. We will have 5 more carbons over here after this, but how this 5 will be there, we have to remember this is the isooctane. So isooctane is having both iso part over here as well as neo part over here, but iso is given more priority or neo, so we call this as isooctane. So this is the structure of isooctane. So if the student is not having this knowledge that this is the structure of isooctane, then it is very difficult to solve this question. Now we are having this monochlorination, and as I told you the different position of hydrogen. Let us see what are the different position of hydrogen over here. This and this position is same. I am giving this a circle. This is different position, I am giving it a square. This is different position, I am giving it a triangle, and these three are same, I am giving it a cylinder. So I can see how many different position of hydrogen are there. This is circle 1, this is 2, this is 3, and this is 4. So we are having total 4 monochloro structural isomeric products obtained over here. Okay, are you getting? These are 4 monochloro structural isomeric product obtained over here. One will be the one which will replace hydrogen from here, chlorine will be substituted, or here or here or any one of the 3. Okay, so total 4 monochloro structural isomeric products will be obtained over here. The answer will be D option. Okay, next, cyclopentane Cl2H, number of monochloro structural isomeric product. So cyclopentane, you can see all the positions are same over here, Cl2H nu. So we are getting only and only one monochloro structural isomeric product over here, because all the position are same, and so that's why only one position of hydrogen is there, and so we will getting only one monochloro product over here. So let us see the next question. Isobutane Cl2H, number of monochloro structural isomeric product, isobutane. So let us draw the isobutane. This is nothing but isobutane. Okay, and they are asking us how many product will be obtained, Cl2H nu. So you can see this is same position, number 1, I am getting it by circle, and this is second position, I am giving a rectangle. So we are having 2 different positions, so 2 products. I am only talking about the monochloro structural isomeric products. So we are only talking about structural isomers over here. So how many will be obtained? 2 will be obtained over here. Okay, next, so this is the question, what will be the product obtained? So you can see over here, this is neopentane, and I can see this all positions are same position over here. They are only having hydrogen. In between, the carbon is not having hydrogen with it. So only one product will be obtained. You can substitute any hydrogen with chlorine, such as like if we are having this CH2 and one Cl will be attached over here. So the answer will be this B option, CH3, CCH3, CH3, CH2, Cl. Okay. So let us continue with the preparation part over here. So we were having preparation of haloalkane from alkane. Now let us see preparation of haloalkane from alkene. Let us see preparation of haloalkane from alkene. So in this we are having two cases. We are having case 1, that is the addition reaction, addition of HX, okay, or addition of HBr in presence of peroxide. Okay, are you getting? So in this addition of HX, we can see we are having RCH double bond CH2 and we are adding HX to it. We will follow the Markovnikov rule over here. I am simply writing MK rule, and everybody knows what happens in Markovnikov rule. We will be having addition of hydrogen to carbon with more hydrogen and addition of halogen to carbon with less hydrogen. So what will happen over here? You will get R CHX CH3. This is the haloalkane we are getting over here. In this, what will happen? Same RCH double bond CH2 we are taking over here, and now we are having addition of HBr, and that also in presence of peroxide. I am writing H2O2 hydrogen peroxide over here. What will happen? We will be following anti-Markovnikov rule over here. So what is the difference? Basically here there will be carbocation mechanism, carbocation, and here there will be free radical mechanism. That is the basic concept over here, free radical. And in this you can see there will be anti-Markovnikov rule. And what is anti-Markovnikov rule? The hydrogen addition will be to that carbon having less number of hydrogen, and bromine will be added to carbon with more hydrogen. So what will happen? What will be the product obtained over here? RCH2CH2Br. So this is the product obtained. This was addition of HX or addition of HBr in presence of peroxide. By this also we prepared the haloalkane over here. I am now talking about the case 2 over here. See, I am talking about case 2 where we will be talking about the allyl position and the benzyl position. Mainly what happens if we are using special reagent like NBS, which stands for N-bromosuccinamide, or NCS, which stands for N-chlorosuccinamide. They are used for halogenation at the allyl and benzyl position. So that is a very interesting preparation method. So let us see case number 2, where we are having halogenation, which can be either chlorination or bromination, halogenation at allyl or benzyl position. So what is this allyl position? Let us first understand. CH3, CH double bond, CH, CH3. So these are the allyl positions. And what is benzyl? Suppose I am drawing a toluene over here. So this CH3 is nothing but benzyl position. See what happens. This free radical over the allyl position or benzyl position is stabilized by the resonance. That's why what will happen, we are having, first of all, let us have for bromination. For bromination, we are using the reagent NBS, where the full form of this is NBS is N-bromosuccinamide. N-bromosuccinamide. What is this N-bromosuccinamide? Let us have the structure of it. See, succinamide means we already studied in the OMS gap. S stands for succinic acid. So this is actually a salt which is obtained by reaction of succinic acid with ammonia. I am giving you the method of how it was prepared. This is nothing but succinic acid, and this succinic acid was reacted with ammonia and followed by the bromination. So what will happen? This ammonia H and this OH. I will give you the explanation properly. C double bond OH, NHH. So from here we are removing the water and there is formation of amide, and after that we are having reaction with bromine, and this is nothing but alpha hydrogen. So this alpha hydrogen will be substituted and you will get this one as the product, and this is nothing but NBS, N-bromosuccinamide, NBS. Okay, this is nothing but NBS, N-bromosuccinamide. Similarly, we can have NCS also, but let us first have the bromination. So just for example I am taking, this is the alkene given over here and we are reacting with NBS. What will happen? This is the allyl position. So if we are having one equivalent of NBS over here, one of the allyl position hydrogen will be substituted by the bromine. Similar in case of toluene also. We are reacting with NBS. What will happen? One equivalent of NBS. This is the benzyl position, and that's why what will happen? One of the hydrogen of the benzyl position will be substituted by bromine. Okay. For bromination we are using NBS. For chlorination, similarly, for chlorination, you can have the use of NCS, which stands for N-chlorosuccinamide. N-chlorosuccinamide, okay, NCS. And what will be the structure of it? This is the structure of N-chlorosuccinamide. What it will do? It will have chlorination at allyl and benzyl position. For example, similarly beta CH2 double bond CH, CH3, and we are reacting it with NCS, one equivalent. What will happen? This allyl position, this hydrogen will be substituted by the chlorine. Again we are having this toluene over here. We are reacting this toluene with NCS, one equivalent. What we will get? Chlorination will be happening at this benzyl position. Okay, so this was the preparation of haloalkane from alkene. In case 1 we had the addition, and in case 2 substitution at allyl and benzyl position. Okay, so let us see questions related to this. Like this question they are asking, Z plus HCl giving this. So basically it will be alkene and addition of HCl has taken place by Markovnikov rule. So it will be having the cyclopentene as a reactant. This, because if you add HCl to this, we will get this hydrogen. We can add to any position. Here actually Markovnikov, anti-Markovnikov, none of them will be followed because both the position are similar over here. So definitely if you add HCl to this, one of the hydrogen will get attached to this pi bond will be broken, and one chlorine will attach over here, and you will get this C option as the answer. Okay, next let us see more questions over here. Now we are having questions from alkene to haloalkane. This is alkene, we are adding HBr. We are not having peroxide, so this is also Markovnikov rule over here. And so hydrogen will be attached to this position, bromine will be attached to this middle position. So our answer will be this C option over here. So let us have next, let us move forward now. So this was preparation of haloalkane from alkene. We are having preparation of chloro and bromoalkanes, you can see, but we never had the preparation for fluoroalkane, or you can say iodoalkane, because these are the extreme points. Fluorine is much more electronegative, it will be having a very vigorous reaction, and iodine, it will be having a reversible reaction. So we must have some methods where we can have specifically synthesis of iodoalkane and fluoroalkane. Which will be the best methods for their preparation? Which will be the best methods for their preparation? So let us see. Preparation of iodoalkane, and as we discuss this, there is a special method for preparation of iodoalkane, that is our Finkelstein reaction. Finkelstein reaction, it is for synthesis of iodoalkane. It is for the synthesis of iodoalkane from chloroalkane or bromoalkane. It is for the synthesis of iodoalkane from chloroalkane or bromoalkane. And what is the reagent used over here? The reagent used over here is NaI in presence of dry acetone. So basically this dry acetone is a solvent over here, okay, and already if you know dry acetone, this is a polar aprotic solvent. So in this case mainly there is possibility of SN2 reaction unless there is 3 degree. Most of the cases we can say directly that it will favor the SN2 mechanism in case of this reaction because we are having polar aprotic solvent. So what will happen over here? What is the reaction about? We are having either chloroalkane or bromoalkane and we are reacting it with NaI in presence of dry acetone. And most of the cases we will be having this SN2 mechanism where this iodine minus will replace this chlorine or bromine. We will get Ri plus the byproduct will be either NaCl or NaBr depending on which, either if you are taking chloroalkane NaCl and if you are having bromoalkane you will get NaBr. So this is the Finkelstein reaction, which is the best method for preparation of iodoalkane. This is the method dedicated for the preparation of iodoalkane, which we call it as Finkelstein reaction. Okay. So let us see questions related to this. This is the chloroalkane they have given over here and we are reacting with NaI in presence of dry acetone. So everybody knows this is Finkelstein reaction. What will happen over here? This iodine minus will attack this and this chlorine will be replaced by iodine. So we will get synthesis of iodoalkane. This will be our iodoalkane which will be produced over here. B option will be the answer. Next question. Z plus NaI reacted in presence of dry acetone and you are getting this as the product. So definitely in place of iodine we will be having, in this Z we will be having either chlorine or bromine. We will be having CH2, either bromine or chlorine. So this is the answer. As I can see, they have given us chloroalkane. So A option will be the answer. So this was all about the preparation of iodoalkane from chloroalkane or bromoalkane, which is our Finkelstein reaction. It is for the preparation of iodoalkane from chloroalkane or bromoalkane. So let us see the preparation of fluoroalkane. Preparation of fluoroalkane. So, like we had dedicated method for the preparation of iodoalkane, we are also having dedicated method for the preparation of fluoroalkane, and which is nothing but Schwarz reaction. We call it as Schwarz or Schwarz reaction. In this reaction, we are having synthesis of fluoroalkanes from chloroalkane or bromoalkane, okay, and the reagent used over here is reagent is nothing but metal fluorides we are using over here, and this metal fluorides can be AgF or Hg2F2 or COF2 or SbF3. Among them you can use any one, okay. So this is for the preparation of fluoroalkane from chloroalkane or bromoalkane. What will be the reaction? Suppose we are having RCl and you are reacting with SbF3 over here. What will happen? You can take 3 equivalents of RCl because it is having 3 fluorines. You can have 3 chloroalkanes converted to 3 fluoroalkanes and the byproduct will be SbCl3. Okay, so this is the reaction and this reaction is called Schwarz reaction. So in this we are having this use of metal fluorides which can be either AgF, Hg2F2, COF2 or SbF3. So let us see the questions. They are having CH3, CH2, Cl plus AgF giving this. So definitely what has happened? This fluorine will substitute the chlorine and you will get CH3, CH2, F as the product, and this is nothing but Schwarz reaction. So B option will be the answer. Next, they have given us this reacted with Y giving this. So this will be a metal fluoride. As we discussed, metal fluorides are used for the Schwarz reaction for preparation of fluoroalkane from chloroalkane or bromoalkane. So as we saw, we can use AgF, we can use Hg2F2 or we can use SbF3. So all of these will be the answer. Next we are having Z reacted with SbF3 giving this. So we already know what would have happened. This will be chloroalkane or chloroalkene, bromoalkene, and what would have happened? This SbF3 provided fluorine minus and it substituted the chlorine or bromine. So in place of fluorine we will be having in this Z either bromine or chlorine. So Z will be like either chlorine will be there or either bromine will be there. Okay, so from this they have given us the chloro one, that is the C option will be the answer over here. So let us now move forward. Now we had the preparation of haloalkane, all methods we studied about. So all methods of preparation of haloalkane we studied, whether it be the first method we had, that is the Darzan method, where we had preparation of haloalkane from alcohols and it was the best method, you remember. Second method was by reaction of alcohol with PCl3 or PCl5. Third method was by reaction of HX with this alcohol in presence of anhydrous ZnCl2, and that was nothing but the Lucas test, Lucas reagent. And then after we prepared the haloalkane from alkane, then after from alkene, and now we had the preparation methods of iodoalkane, which is the Finkelstein reaction, and after that we had the preparation method of fluoroalkane, that is the Schwarz reaction. Now let us have reactions of haloalkane. Reactions of haloalkane. So in reactions of haloalkane, first of all we will be having reaction with KNO2. If we are reacting haloalkane with KNO2, see this KNO2 is having ionic nature. So in this what will happen? O minus will attack KO minus and double bond O. This O minus will attack and you will get RO and double bond O. But instead of this KX, if we are reacting with AG KNO2, instead of this KNO2 we are reacting with AgNO2. See this AgNO2 is having covalent character. Everybody knows the Fazan's rule. Pseudo inert gas configuration cation like Ag plus is having pseudo inert gas configuration, and the cations having pseudo inert gas configuration show very high polarizing power, so they are having very high covalent character. So this AgNO2 will be having a very high covalent character. So in this case the nitrogen lone pair are going to play a very important role. This time this nitrogen lone pairs are going to attack and we are going to get RNO2 as a product. Okay, so this was all about reaction with KNO2 and AgNO2. Similarly we can have reaction with KCN and AgCN. With KCN, with what will happen? Rx reacted with KCN. This is also ionic, K plus and Cn minus. Cn minus will attack over this R and will substitute the X, then we will get RCN plus byproduct will be Kx. Instead of KCN, if we are having AgCN, similar thing will happen. Everybody knows Ag plus 1 is having pseudo inert gas configuration. Pseudo inert gas configuration, that is nothing but everybody must be knowing NH2, NP6 and D10. This is nothing but the pseudo inert gas configuration, and according to Fazan rule, the cation having pseudo inert gas configuration is having very high polarizing power. So all the Ag plus 1, that's why the Ag plus 1 salts are sparingly soluble, because they are having very high covalent character. We are reacting this with AgCN. So this time what will happen? Because of the covalent character, this time the lone pair have to attack. This lone pair will attack and we will get R and C plus AgX as the byproduct. So we are getting in this cyanide, or you can say nitrile in IUPAC, and this we are getting isonitrile or isocyanide as the product. So this is the reaction of haloalkane with all the three KNO2, AgNO2, KCN, AgCN. The main thing over here is Ag plus salts are having covalent character, because in Fazan's rule we have studied Ag plus is having the electronic configuration 4s2, 4p6, 4d10, which is nothing but NH2, NP6, ND10. We call it as pseudo inert gas configuration, and they are having very high polarizing power. So all these Ag salts we generally see, they are having high covalent character. So now we can have one more reaction over here. I can prepare the alcohols from haloalkane, and there is a very interesting method where we will be having first preparation of Grignard reagent from the given haloalkane, and we can have preparation of all the three, 1 degree, 2 degree or 3 degree alcohol. Let us see this method of preparation of alcohol from haloalkane. So you can treat it as a reaction of haloalkane, as well as it will be a preparation of alcohol. So what is going to happen? We are having suppose Rx haloalkane, and we are reacting it with Grignard, this Mg to prepare the Grignard reagent, Mg in presence of dry ether. We are first preparing the Grignard reagent. We are getting R minus Mg plus 2 X minus, this is our Grignard reagent. This is our Grignard reagent. And from this Grignard reagent, we can prepare all the three alcohols 1 degree, 2 degree or 3 degree. So let us see case 1. Let us have the preparation of 1 degree alcohol. So what we are going to carry out? We are having this Grignard reagent R minus Mg plus 2X minus. First of all, we will react it with HCHO, formaldehyde. The smallest aldehyde, formaldehyde, we have to react it with formaldehyde. What will happen? This R minus Mg plus 2X minus, this is having a nucleophile. It will attack as a nucleophile on this C double bond position, and you will be getting RCH2O minus Mg plus 2 X minus. And after that we are having acidic hydrolysis. You can say H3O plus, which will provide H plus over here, RCH2OH. So we are getting 1 degree alcohol over here, as you can see. So this was preparation of 1 degree alcohol. Similarly, we can have the preparation of 2 degree alcohol also. For the 2 degree alcohol case 2 I am talking about. In this we are having a reaction of Grignard reagent R minus Mg plus 2 X minus with, this time we will be having higher aldehyde R C double bond OH. It is not, R is nothing but a higher CH3, or you can say CH2 CH3, means this R cannot be H. This is higher aldehyde, and this R minus again will behave as a nucleophile over here. This R minus will attack this C double bond position. It will shift upward, and you will get RCO minus Mg plus 2 X minus RH, and again the acidic hydrolysis H3O plus, which will provide H plus RCOH RH. So you can see this carbon is 2 degree, so the OH is also 2 degree. We got 2 degree alcohol over here. Okay, so just what we change, instead of formaldehyde we use the higher aldehyde, and we are getting the 2 degree alcohol. Now let us have the preparation of 3 degree alcohol over here. 3 degree alcohol. So you saw you are having R minus Mg plus 2 X minus and reacting with R C double bond O R. This is nothing but ketone. Now we are having ketone. In place of higher aldehyde, I took the ketone. This is nothing but again Grignard reagent will act as a nucleophile, will attack this position, it will get shift upwards, you will get RCRRO minus Mg plus 2 X minus. And then we are reacting it with H3O plus. What will happen? Instead of Mg plus 2 X minus, you will get H attached over here, RCRR, and we are having OH. So this is 3 degree carbon and OH attached to it. So this is 3 degree alcohol over here. So you can see we prepared all the three 1 degree, 2 degree and 3 degree alcohol over here. Okay. So this was a very interesting preparation of alkane, alcohol from haloalkane. So let us see the questions also. So they are asking, we are reacting with KNO2. Already I told you this NO2 minus O minus will attack over here, and what will happen? This O minus will attack and it will replace the Cl. We will get the first option as the answer. Next, AgNO2. So this nitrogen lone pair will attack and here NO2 will be attached. So B option will be the answer. Okay. Let us have question related to alcohols. This is the question. Which carbonyl compound is used for the following interconversion? So this is nothing but Grignard reagent and reacting with carbonyl group, which can be aldehyde or ketone, and followed by H3O plus. You are getting this. As you can see, this is 3-degree alcohol. So definitely this is only possible if this carbonyl is a ketone. We already studied this now. So this ketone is reacted with this CH3CH2 MgBr, and then after that we are getting this. So what will happen? Let us see this ketone be this acetone. CH2 minus is attacking over here, it is getting shift, and we are getting CH3 CH3O minus Mg plus 2 X minus, and CH3 CH2 CH3 is getting attached, and this after this we are having acidic hydrolysis as they have told over here, and this will provide the H plus, and we are getting CH3 COH CH3 CH2 CH3. So this is the same product we are getting over here. So definitely, as I told you, by looking at 3-degree alcohol, you will already think that ketone should be the reactant over here, because 3-degree alcohol, we already now only studied that for preparation of 3-degree alcohol, we have to react with ketone. Okay. So this was all about the preparation of alcohol. We are having many more sections, but as we already see, we are having extension of time, and we discuss many important preparation of haloalkane, preparation of alcohol, and their questions over here. It was a very nice discussion. Thank you for coming over here to this power hour session. So let us meet in the next power hour session. Thank you, dear students.